We've dealt with roots, square roots, cube roots. We've dealt with exponents, but here we combine them into what are called nth roots and rational exponents. And so a rational exponent just means that it's an exponent that is a fraction. A rational expression is just code for a fraction involving a variable. And so if we have a fraction for an exponent, like a being raised to the 1 over n power, that's a different way of writing that we're taking some sort of root, the nth root, from the name nth roots here. So if it's a to the 1/7 or x to the 1/7, like what we see here, what that means is we're taking not the square root of x, but it's the 7th root of x. So whatever the number in the denominator is, that slides in as the root that we're taking of whatever the base is. So in this case, it's the 7th root of x. If this was 1/5, then it would be the 5th root of x. Now, we are not always going to see a 1 in the numerator of the fractional exponent. Instead, sometimes we'll have some other number. Well, that will become the exponent on the number underneath the radical symbol. So you can see here, just like in the previous example, the denominator of the exponent stays as the root, but now the numerator in the exponent is going to be the exponent on the base underneath that radical. And so we can see that in this second example. So here I've got 9 is going to be underneath the root symbol. It's going to be squared because the numerator has a 2 in it, and then it's going to be under a 5th root symbol because the denominator of the exponent has a 5 in it. And so then we can go ahead and multiply out that 9 squared, so we get the 5th root of 81. For this second example, or this last example I should say, we have a to the 3/4. So again, the numerator becomes the exponent on the base, so a cubed, and then the denominator becomes the root. So it's going to be a cubed, and then underneath a 4th root. And then for the second part of it, we have b. It's going to be to the 1st. So I can just leave it as b or write it as b to the 1st. And then again, because the denominator of the exponent is 4, it's going to be the 4th root of b. And so since I've got the same root in both parts of my expression, I can go ahead and combine those into a single 4th root with both parts underneath that root. So I've got a cubed times b underneath the same root symbol. It's just a little bit cleaner presentation of that answer, a little bit simplified. So again, the idea here is whatever number is in the denominator of the exponent is going to be the root. Whatever number is in the numerator of the exponent is going to be the power on the variable underneath that root. And so in the next set of examples, we're just working in the opposite direction. So now instead of being given the expression in exponent form and writing it as a radical, now we're taking the radical form and writing it as an exponent. So the same rule applies. So if we concentrate on this x part first, so it's going to be x to the, and then the exponent on the x there is going to be in the numerator of my exponent, while the root is going to be in the denominator. So since it's the 6th root, it's going to be x to the 5/6 power. And then in the case of the y, it's going to be the same idea. So the exponent on the y, even though it's not written there as 1, the root is 6, so this is going to be raised to the 1/6 power. And for the last example, we shouldn't get distracted by the fact that we have a fraction instead of it just being in the numerator for the radical expression. So I'm just going to make sure that it's 1 over my expression. So again, x, now the exponent on the x there is the 2, so that's going to go into the numerator, and then the denominator is going to be the root, so that's 3. So I've got x to the 2/3 power, and then that's just in the denominator. Now under normal circumstances, we would not leave our answer like this because this is the equivalent of leaving a root in the denominator, but we'll deal with rationalizing denominators, getting the square root out of a denominator in a situation like this for a later time. The important thing here is to make sure that we're able to rewrite it in exponent form, having been given the radical form. Now when given a number that's raised to an exponent instead of just a variable, then there's potentially some more simplifying that has to happen. So in this first one here, where we've got 4 to the 2/3 power, I'm first going to rewrite it in radical form, and then I need to see if I can get anything out from underneath the radical. I couldn't really do that on any of the previous examples, but here we're going to be able to. So again, it's going to be a 4, and then I'm going to have squared, since that's in the numerator, and then that's underneath the cube root symbol, since the 3 is in the denominator. So if I expand that now, I've got the cube root of, now I'm not going to multiply 4 squared out, instead I'm going to leave it as 4 times 4, because now I'm going to try to see if there's anything I can get out from underneath the radical. Now because it's a cube root, I don't need pairs of numbers or perfect squares, I need cubes. I need triples of numbers or perfect cubes. So I'm going to factor tree each of these 4s down into a pair of 2s. And so now we can see we got 1, 2, 3 2s here. We've got 4 of them, but it takes 3 to get something out. So I'm going to take that 2 out. So all of those get wiped out, but I still have a 2 that's trapped underneath the radical symbol. So it's going to be 2 times the cube root of 2. So that's my simplified answer in this case. In the second example, we're going to start off again, do the same thing. We're going to rewrite it in radical form, and then I'm going to look to see if I can get anything out from underneath the radical. So I've got -2, and then that's going to be raised to the numerator, so to the 5th power, but then that's going to be underneath a radical symbol that tracks with the denominator, so it's going to be the cube root of that. So I'm going to write this out the long way. I'm going to have -2 times -2. I'm going to have 5 of those, since it's being raised to the 5th power. I'm not going to bother to multiply that out, because again, I'm looking to see if I can get a set of 3 of them so that I can pull it out. And indeed, I've got that right here. So I've got a set of 3 -2s, so I'm going to be able to get that out from underneath the radical symbol. So I'm going to have a -2 on the outside, and then trapped on the inside underneath my cube root symbol are going to be the remaining couple of -2s. But I'm going to go ahead and multiply those together just to simplify. So -2 times -2 gives me +4. So again, I'm looking to see if there's anything that I can get out from underneath the radical in order to simplify, just like we did with square roots and cube roots earlier. So for the next one, following the same pattern, so I've got 9, the numerator is 3 on the exponent, so it's going to be 9 cubed, and then that's going to be underneath a square root symbol. So in the case of square root, I can choose to put the 2 there or not. So I'll leave that off for now. So I've got 9 times 9 times 9. And so remember, we need a pair of something underneath the square root symbol. So I've got a pair of 9s here. So I'm going to be able to get a 9 out from underneath the square root symbol. And then I still have the square root of 9. But hopefully we're recognizing that 9 is a perfect square, or we could factor tree that into 3 and 3, which means I'm going to be able to get a 3 out as well as the 9 that I already have on the outside. So I'm going to have 9 times 3, which gives me 27. So in this case, we were able to get everything out from underneath the root symbol and just ended up with a whole number of 27. And then for the last one, if we jump there, so -25 is our base, so we've got that to start with. The numerator of the exponent is a 2, so I'm going to put a 2 as the exponent there, and then it's going to be underneath a cube root symbol. So I'm going to expand this expression here, so I'm going to have -25 times -25 underneath that cube root symbol. So I don't have a set of 3 25s, but I can factor tree this down because 25 can be multiplied into 5 times 5. The other thing I'm going to need to do here is I'm going to separate those root -1s. So I'm going to have the cube root of -1 times -1, and then I'm going to factor tree these 25s, which gives me 5 times 5 for the first one, and then times 5 times 5 for the second one. So I'm just separating out those root -1s because those are going to multiply each other to make 1, so I don't have to worry about that. And so now I've got a set of 3 5s underneath the square or cube root symbol. So I'm going to be able to get a 5 out. And then I've got 1 5 that's left over, so that's going to be still trapped underneath that cube root symbol. So the cube root, oops, not the 5th root, but the cube root of that remaining 5. So there's our simplified answer. So again, after rewriting it in radical form, if we can get anything out from underneath the root symbol, we have to make sure to do so. Sometimes we have to do a little factor treeing to help us along.